Take a look at this graphic. Down here is the explosive yield of the bomb dropped on Hiroshima in 1945, and expanding outward, towering over it, represents the combined power of the 12,500 nuclear warheads sitting in modern arsenals today. Every single one of these modern weapons is roughly 80 times more powerful than that original bomb. To understand what that scale actually means, look at this photograph of Hiroshima. A single, primitive device erased an entire city in seconds, killing 70,000 people instantly, and leaving only a flattened, scorched expanse of debris in its wake. It's easy to look at the massive stockpiles held by distant superpowers and think that a conflict between them wouldn't reach you. The logic assumes that if two nations on the other side of the planet launch their arsenals, the physical blasts and the immediate radiation stay confined within their borders. But the localized explosions are only the beginning. The real threat is a concept in environmental science known as nuclear winter. A massive conflict generates a dense, suffocating cloud of soot that rapidly expands across the globe, blocking out the sun and plunging the planet into a deep, artificial freeze. In a modern nuclear exchange, geography offers no protection. You might be thousands of kilometers from the nearest blast zone, but the resulting collapse of the environment means no clean water, no sunlight, and the immediate death of the global food chain. There are no bystanders. The first step toward modern nuclear warfare took place in a German laboratory in 1895. Wilhelm Röntgen was experimenting with a cathode ray tube wrapped in black cardboard. Even with the machine completely shielded, he noticed a cataclysmic plate across the room was glowing in the dark. Röntgen realized an unknown invisible energy was passing right through the solid cardboard. To prove it, he had his wife place her hand on a photographic plate and bombarded it with these mysterious rays. This image is the result, a dark metallic ring and the stark skeletal structure of her hand. He called them X-rays. That image set off a scientific scramble. In Paris, Henri Becquerel wondered if certain glowing rocks could naturally emit these same rays. He wrapped a piece of uranium and a photographic plate together and stuck them in a dark drawer. A few days later, the plate was fogged with clear markings. The uranium rock was generating its own energy out of thin air. Listening to Becquerel lecture, Marie Curie took the next step. She began testing tons of uranium ore to see what else might be hiding inside. Her rigorous chemical analysis led to the discovery of two completely new, highly radioactive elements, polonium and radium. Each scientist was simply pulling at a loose thread to see how the universe worked. They were passing the baton in a relay of pure curiosity, entirely unaware that their discoveries were laying the groundwork for an infinite and lethal source of power. Albert Einstein's 1905 publication of E equals mc squared provided the mathematical basis for nuclear energy. The equation proved that mass could be directly converted into pure energy, explaining why radioactive elements leaked mass as radiation. Shortly after, Ernest Rutherford mapped out exactly where that mass was located. He proved that 99.9% of an atom's mass is locked inside a tiny, incredibly dense core called the nucleus. Accessing the energy Einstein calculated requires breaking into Rutherford's nucleus. However, the nucleus is packed with positively charged protons that violently repel any other positive charges, creating a nearly impenetrable barrier for the particles physicists were using at the time. In 1932, James Chadwick discovered the key, the neutron. Because it has no electrical charge, it doesn't get repelled. As this animation shows, a neutron can slip right past the atom's positive defenses, strike the dense core, and shatter it. And when the atom splits, it releases 3 more neutrons. Now look at the expanding graphic. Those 3 neutrons strike 3 more atoms, releasing 9 neutrons, then 27. Leo Szilard recognized the mechanical reality of this equation. It was the blueprint for a self-sustaining, exponential physical chain reaction. Szilard knew that if this physical process was harnessed, it would create an explosive force unlike anything in history. Fearing that fascist Germany would build it first, he convinced Einstein to warn the US president. That single letter launched the Manhattan Project, instantly shifting atomic science from academic observation to weaponized engineering. But a chain reaction was still just math on a chalkboard. To prove it worked in the physical world, Enrico Fermi built a reactor in a basement beneath the University of Chicago. He slowly withdrew the control rods, the Geiger counter clicked rapidly, and he successfully achieved the first controlled nuclear chain reaction. With the math proven, the Manhattan Project rushed to build an uncontrolled bomb. But physicist Edward Teller ran calculations that stopped the team cold. The Earth's atmosphere is 78% nitrogen. Teller feared the bomb's extreme heat could ignite that nitrogen, setting off a chain reaction that would burn away the entire atmosphere. Hans Bethe, the project's chief calculator, ran the numbers multiple times. He concluded the chances of igniting the atmosphere were almost zero. Not strictly zero, almost. Robert Oppenheimer and the military leadership looked at that tiny margin of error, accepted the risk of global annihilation, and proceeded with the first test anyway. The atmosphere didn't burn, but the local devastation was far worse than a simple shockwave. When the bomb dropped on Hiroshima, the extreme heat created a massive vacuum. This cross-section shows how that rapidly rising hot air violently pulled cold, oxygen-rich air inward from the edges of the city. It created a looping, self-feeding vortex of wind and flame, known as a firestorm. The scientists gambled the Earth's atmosphere and won, but they had successfully mastered the physical chain reaction to build the ultimate city-killing machine, and soon they wouldn't be the only ones to have it. By the Cold War, the physical chain reaction of the atom had evolved into a geopolitical chain reaction. The superpowers built massive stockpiles governed by mutually assured destruction. The Soviet Union even automated their retaliation with a system known as Dead Hand, designed to automatically launch their entire arsenal if their leadership was wiped out. While the militaries plotted targeting coordinates, a physicist named Luis Alvarez was studying 65-million-year-old rocks. He found rare iridium deposits and theorized that a massive asteroid impact had kicked up enough thick dust to block the sun, collapse the food chain, and wipe out the dinosaurs. In 1983, a team of scientists, including Carl Sagan, asked a terrifying question. What if a nuclear exchange did the exact same thing? Look at this photo of Sagan taking these findings public. He took classified doomsday physics and turned it into an urgent environmental warning. This animated graph illustrates their findings, known as the T-TAPS paper. If 5,000 nuclear warheads detonate, the resulting firestorms would launch 1 billion tons of black soot, high above the rain clouds. As the soot metric rises, watch the temperature line plummet. The smoke blocks up to 90% of the sun's light, dropping global average temperatures to -25°C for years. The climatic chain reaction following a nuclear exchange systematically shuts down the Earth's biological life support systems. Weeks after the initial radiation fades, the atmosphere continues to stifle the planet's ability to sustain life, making the environment more lethal than the explosions. You don't even need 5,000 warheads to trigger this. In 2006, scientist Alan Robach ran the climate models for a regional, geographically isolated conflict, like an exchange between India and Pakistan. His research proved that even a limited nuclear exchange would eject enough soot to trigger a catastrophic global winter. Surviving the aftermath requires extreme infrastructural preparation. The electromagnetic pulses from the blasts would fry electrical grids instantly. Protecting power and communication lines requires shielding critical infrastructure inside massive Faraday cages, a step reserved for military targets. When the sun is blocked and surface agriculture dies in the first week, humanity has to pivot underground. It requires shifting entirely to subterranean vertical farming. You'd have to rely on fast-growing crops like spirulina, a high-protein algae grown in dimly lit concrete bunkers. A tiny fraction of humanity with access to deep bunkers and strict rationing might endure the long freeze, but a nuclear war cannot be won. Defeating the enemy means destroying the exact climate you rely on to survive. The only way to survive the final chain reaction is to make sure the first domino never falls.